for?
So this assembly was designed for the nuclear industry. It's been used in an application that's handling irradiated CO2, 54 bar and 425 degrees C. And this particular application is designed to take a valve from the fully closed position to the open position and back to the fully closed position in less than 1 second. And it does that to send a slug of irradiated CO2 down a pipeline to clean a filter element.
Fantastic.
I think for us one of the biggest challenges is that the client didn't have a design brief for us on how to achieve the result that they were looking for. And one of their main conditions, because it was nuclear, is that it has to be extremely reliable. And so for us, obviously, we had to come up with a logic from scratch. As discussed, the key factor for us was reliability. Obviously, to take the valve from fully closed to open to closed in less than 1 second is no easy task. And so we had to focus on certain key vendors who we work with, who we know his equipment is extremely reliable and can help us achieve the result that we're looking to achieve for the client. One of the key factors for them being nuclear is that obviously they assess everything, and so the process of from quotation to order was protracted in the design brief. You're talking about 12 months.
Okay. Site.
This type of equipment, believe it or not, will only be used probably once every 6 weeks, and that in itself brings challenges in that when you have a piece of equipment that's used every day, the probability of failure on demand is very low because you used it just yesterday. If you in 6 weeks' time, will it work on demand? It's a big question. And so for us, we had to take a lot of care in our design, thinking about the infrastructure and the equipment used to make sure that it will work on demand and achieve the result that the client requires.
Okay, fantastic. Solution.
We sat down with the clients and basically on a consult basis to work with them to understand basically what they were trying to achieve and how they wanted to do it. So for example, this is a pneumatic system, so we had to say, we need to use pneumatics. Do you have pneumatic infrastructure available? Obviously, you can imagine on a big site, there are a lot of variables in that. So we had to design in the reliability into this. And for one of the key factors for us was that we used an air tank in the system. And the air tank here was to ensure that we had sufficient volume of air to meet the demand of the actuator. You could imagine on the site if they had an air leak or a demand somewhere else, causing a bit of starvation of air at the part of the plant where this piece of equipment is installed. If they said go and it wouldn't work, there'd be a massive issue, or there would be a big event on the site. So we had to have a lot of foresight into what we needed to provide to ensure that regardless of what happens on the site, this will work. And this system is very, very reliable from that particular perspective, in that if it lost air or it loses power, it will do what it's meant to do regardless. So the client for us, there's a very, very detailed design brief was created by us and approved by the client in the end.
Okay.
No, I think we have a lot of expertise in-house that we've you just gather over the years doing similar type of applications, and we brought that expertise to the meeting. The client obviously know their process very well, and so they know what materials of construction. So when you're nominating materials forward, their engineers are looking at it under the microscope to make sure, based on their experiences on their site, if what we're proposing is actually suitable. And you go through a process like that, which I said is a protracted process. It takes about 12 months being nuclear for them to actually get to a point of actually accepting what we're proposing, accepting the equipment that we're proposing, and then obviously from that we develop a 3D model. And they then start checking the 3D model itself, going through it, making sure that everything that we've designed in will actually work, because they obviously have a responsibility on site to make sure what we're proposing is fit for purpose. Obviously, being nuclear, they check everything.
Solution.
Well, basically we have a 180-degree rotary actuator here that basically takes the valve from the closed to the open to the closed position. And we're also engineered in some special volume boosters which
And how does this project compare with the many other projects that you've been involved with?
This is unique, obviously, in that most of our valves spend their life open or closed, and we might take it to a fail-safe open or closed position depending which state the valve's in a quick operating time, maybe 1 second or 2 seconds, depending on the size of the valve. This is unique in that it went from closed to open to close in less than 1 second. But all the logic and principle we've done before in some way or another. This is the unique thing about Newton, is that a lot of what we do today is similar to what we've done before. You know, we've had a lot of experience on the products, the type of actuators, the type of controls. We have good relationship with those vendors. And so a lot of it for us is the R&D element is removed in that we understand the risk. And having done similar things before, we're confident that we can engineer these solutions quickly, on time, and most importantly, that it does what it says on the tin. It will work. Allow us to control both the flow rate and the pressure in the actuator very, very accurately. And one of the key things that they were worried about was, you can imagine operating so quickly, it can look quite violent. And if you see anything that's operating violently, you'd be worried about reliability. By engineering in the volume boosters effectively, by we control the pressure on both sides of the pistons throughout the stroke. And by doing that, it almost looks like it's in slow motion, even though it's operating so quickly. It's so gentle, the action. And so the client, it was quite important and impressive because they can see by virtue of the way it operates that this valve will be there for a long time, to such a degree that we've actually given them a 3-year unconditional warranty on the equipment.
Okay, fantastic. Journey.
Well, as you can see, we've carried out a function test here at our works to prove that the logic works. The next phase for us is to ship this to the valve maker. The valves themselves, obviously, they're handling the actual process media, the high pressure, high temperature irradiated CO2, which is almost like it has the same consistency as porridge at that pressure and temperature. And one of their main concerns with the valve itself, the pressure containing parts, were absolutely bulletproof. And so the valves have been subjected to extended hydrostatic pressure tests, 150 bar for 24 hours, and to make sure there's absolutely no leaks anywhere, because they can't tolerate any leaks. That would be deemed as almost a catastrophic failure for the plant. And so once they've done that testing, we're going to actually fit the controls, the actuator controls, to the valves. And then to prove that the system works under pressure, the valves will be pressurized to 54 bar, and we'll prove that they still go from closed to open to closed in less than 1 second. And so the client then has full confidence in the equipment that it will work on demand, under pressure, because they've seen it physically happen at test. I would say this will be installed in the plant within 3 months of the test, final testing, the factory acceptance test they call it. We should, being nuclear, they have to wait for an outage, an opportunity effectively to fit the equipment into the pipeline safely. There's a lot of anticipation to get this in, so we would imagine that from conclusion of the tests within 3 months. This actually was for us quite a unique feature in that, because the design brief and the design stage was so protracted with the client to get all the equipment approved, when they gave us the order, we were physically able to have this ready for testing within 16 working weeks. Normally in the nuclear industry, they're used to protracted lead times from some of their sub-vendors of anything up to 52 weeks. So for us to be able to produce this in 16 weeks from given the physical purchase order, for them was unique. That was quite amazing. So we hope that, and that's something that's unique to Newton really, is that we're able to engineer bespoke solutions, but in probably half the lead time of a lot of our competitors. And that was one of the key factors for them in selecting us, was not only the capability, was the fact that we could actually deliver this equipment in a really quick lead time once they actually gave us the purchase order.
Fantastic.
This is unique, obviously, in that most of our valves spend their life open or closed, and we might take it to a fail-safe open or closed position depending which state the valve's in a quick operating time, maybe 1 second or 2 seconds, depending on the size of the valve. This is unique in that it went from closed to open to close in less than 1 second. But all the logic and principle we've done before in some way or another. This is the unique thing about Newton, is that a lot of what we do today is similar to what we've done before. You know, we've had a lot of experience on the products, the type of actuators, the type of controls, and we have good relationship with those vendors. And so a lot of it for us is the R&D element is removed in that we understand the risk, and having done similar things before, we're confident that we can engineer these solutions quickly, on time, and most importantly, that it does what it says on the tin. It will work.
Fantastic.